So today, Professor Jeffrey Teo, we're gonna talk about the theoretical survey of the bosonic topological phase in 2+1D in the perspective of emergent and Diracand and Majorana fermions. So please go ahead.
Oh, thanks. So first, I would like to thank the organizers for inviting me to give a talk of this wonderful workshop. And also thank Munjib for giving me a very nice introduction, maybe I would say probably even too nice. So today I would like to give a story. So this is a theoretical story of a family of bosonic topological phases in 2 dimensions. So the title I call a theoretical survey, but to be honest, I would rather call it a theoretical speculation because at this point, there's no known materials to support these 2-dimensional topological phases. But hopefully in the future, there are some interesting phases that emerge from this line of thinking. So first, I will begin with an introduction of defining this family of bosonic topological phases. So these are chiral phases in the sense that there's a bulk boundary correspondence. So there's a bulk energy gap in the bulk of the material, but on the edge, there's a gapless chiral theory that runs along the boundary. So the most important keyword is bosonic. So throughout this talk, I'll only focus on phases that are constructed from electrons. So we all know electrons are fermions. So there is a notion of what do we exactly mean by bosonic topological phases constructed from electrons. I'll first need to define this notion before I can move on. And the main part of the talk is going to be divided into 2 parts. The first part is to introduce the E8 quantum Hall state. So this is really a bosonic analog of the field lowest Landau level, except the difference, of course, it is bosonic. As I was saying before, I will define the notion of bosonic topological phases in more detail later. So the construction is going to rely on an exactly solvable model, couple Y model, which gives us an exactly solvable Hamiltonian for us to be able to theoretically study this state. Although this model is not designed to understand the energetics favorability for these states to arise, but let's it give us some exactly solvable model, a Hamiltonian that we have some handle on. And finally, I'll focus on some transport properties that defines this E8 quantum Hall state. And the second part of the talk is to look at the fractionalization of such state. So in the first part, I'll make the connection or the analog of the E8 quantum Hall state as the bosonic analog of the field Landau level. So the most obvious way to generalize or to move forward is look at partially filled, partially filling this state. So for example, for Landau level, if we partially fill the Landau level, we get the Latin 1/m state, for example. So there's also a notion of fractionally filling the E8 quantum Hall state, and this leads to some long-range entangled topological states. And there's a family of them, and I'll try to present that family in this talk. So in particular, it makes use of the Wessel-Minowitten subalgebra structure of E8, and also there's a particle-hole conjugation structure within the family. Finally, I will conclude and maybe make relations to some other bosonic phases. So let me introduce the concepts of topological phases, and in particular bosonic ones that are constructed from electrons. So chiral topological phases has the following features. So first, it must have a bulk energy gap. So delta G here is the finite bulk energy gap that is bigger than 0 as the thermodynamic limit. So what it means is that if we focus on the diagram below at the middle, or numerically, if we compactify the model on a closed surface without boundary, that there must be a bulk energy gap that separates the ground state. So the lowest, in this diagram, the lowest 3 levels are the ground state, and then above which there is a finite energy gap of delta G that separates the ground state from all the excitation states. On the other hand, if we have an open boundary, so this happens, for example, on the left diagram, if we if we place the topological phase on a disk with an open circular boundary, or in the Rice diagram, if we place the topological phase on an open cylinder with the left and right circular boundaries. In these cases, there will be gapless chiral modes that runs along the boundary. So for example, on the left case, there's a chiral conformal field theory that runs along the boundary of the disk. And here on the cylindrical geometry, there's going to be the left and the right boundaries, both of which contain some boundary modes. So in this case, the energy diagram looks quite different. So there's also going to be the ground states. There's going to be a bulk state, which has this gray levels. But in between mid-gap, there will be some states that corresponds to modes that runs along the boundary. And in low energy, they corresponds to an edge conformal field theory. So these type of phases appeared in integer or fractional quantum Hall states. They also appears on some chiral spin liquid or some topological superconductors. We'll rely on a notion of bosonic topological phases that are constructed from electrons. So electrons are fermions. So in this case, we have a many-body local Hamiltonian of electrons. What it means is that it's a Hamiltonian operator that is built out of electrons, and the interactions only couple electrons locally. And the second requirement is that is a requirement for it to be called a bosonic topological phase, is that in addition to the energy gap that we introduced in the previous page, we have, in addition to that, a fermion gap. So this delta GF is not the energy gap that I introduced previously. It's a second energy scale. So it has to be finite, so non-zero in the thermodynamic limits, so that below this energy scale, delta GF, the fermion gap, there is no local fermion excitations. So if I look at the diagram on the left side here, so here I'm taking either the open cylindrical geometry or the disk geometry, both of which have open boundaries, and therefore there will be gapless edge modes. So there is going to be two energy scales. So there's one energy scale that separates the edge from the bulk excitation. So that's the bulk energy gap delta G. And then there is another energy scale, delta GF, so that's the fermion gap. So below this fermion gap, all these energy levels, they're either fractional, or if they're not fractional, if they're integral, then they must be bosonic. So all the states below delta F, if they're local, they must be bosonic, meaning that they must be even electron combinations. So above this energy fermion gap, there could be local fermion excitations that appears. So in particular, if you look at the edge, this means that all the local edge excitation must be bosonic. Again, there might be some fractional excitations, but if I only take integral excitations, then they must be bosonic on the edge. All right, so under this requirement, then we can make distinctions from more conventional fermionic topological phases. So these are four examples with the first field lowest Landau level, or conventional integer quantum Hall states, or Chern insulating states, or the fractional Laughlin quantum Hall states, or the Morley-Paphian state. These are all fermionic states which are not bosonic because there is no finite fermion gap for any of these conventional phases. So the fermion gaps goes away on the edge in the thermodynamic limit where the system size grows to infinity. So finally, in the introduction section, I'll maybe define the notion of topological order, or separate into two classes. So one is short-range entangled, and the other one is long-range entangled. What this means is that short-range entangled just means that it is an integral phase, and long-range entangled just means that it is a fractional one. So for example, in the short-range entangled state, if you put the topological phase on the closed surface, the ground state is non-degenerate, so you only get one and only one ground state. On the other hand, for the fractional version, the long-range entangled one, if you put it on a high genus surface with genus bigger than 1, like a torus, then you would have a degenerate ground state at the bottom. So the short-range entangled states does not supports fractional excitations. This means that all excitation must be integral combinations of the electrons, and this means that they must be either bosonic or fermionic. On the other hand, for long-range fractional topological phases, then the excitation could be fractional. What it means is that the fractional anionic excitations must come in conjugate pairs. So you can look at this diagram here, for example, where I have two excitation A and A bar that are separated in space. But if one wants to create such an excitations, you must apply on the ground state a long electron strings that connect the two. So these are non-local anionic excitations that carry some anionic statistics that doesn't look like bosonic or fermions or fermionic. All right, so that's the introduction. So maybe now I can move on to the E8 quantum Hall states. So this is a bosonic analog for the field lowest Landau level. So maybe I should spend 1 or 2 pages on reviewing some key features of the field lowest Landau level. So this happens to be an integer quantum Hall state with filling 1. So filling number by definition, of course, is the number of electrons divided by the number of flux quantum. So that's the integer quantum Hall phase, but there are some similar phases that are related to the field lowest Landau level. So for example, on the left diagram here, that's the Chern insulator or the quantum anomalous Hall states. So this diagram is the Haldane honeycomb model. And on the right diagram, there is a 3D slab geometry, a thin film geometry of a topological insulator, where on the top and the bottom surface, we put on some magnetic impurities to introduce a magnetism and therefore open up the surface Diracand mass gap. So in this situation, in the quasi 2-dimensional limit, you can think of this thin film with magnetic top and bottom surfaces being a equivalent to a Chern insulators. So the key features of the field lowest Landau level or Chern insulator is that it's a chiral short range entangled topological phase. So it satisfies all the criterion that I listed previously. So it has a bulk energy gap. So in this case, for the Landau level, the energy gap is given by the cyclotron frequency. And there is a gapless chiral fermion edge mode. So in this picture right here, you can see that in the bulk, they basically just the electrons that stands in cyclotron orbits. But then on the edge, there's some skipping orbits, and that suggests that there are unidirectional propagating fermions that propagates along the edge. So on the edge, you basically have a unidirectional propagating massless fermion. And the states are pretty easy to understand. It can be simply understood by single body non-interacting electrons. So all the excitations are electronic, so they're integral combinations of electrons. There's no fractionalization, and therefore the ground state is non-degenerate no matter how you put the system on any closed surface. On the other hand, this state is fermionic, obviously, because there's no fermion gap. But there's no fermion gap on the edge in particular. So on the edge, you can find in the thermodynamic limits any arbitrarily small excitations that are fermionic. So there's no fermion gap, and therefore this is not a bosonic state. So what we want to focus on today is to find the bosonic analog of the field lowest Landau level. So meaning we want to find a topological phase constructed from electrons, but we want the edge of this chiral topological phase to carry a fermion gap. So there's a gapless edge mode, but then there's a fermion gap dictating that below the fermion gap on the edge, all local excitations must be bosonic. So maybe in the field lowest level, we can also discuss some transport property. In particular, I want to point out the thermal and the electric Hall conductance, the transverse conductance. So on the left diagram, it tells us the transverse conductance of the lowest Landau level. So in this case, the filling number is 1, and the transverse conductance is 1 times E squared over H. And on the right diagram is the diagram for thermal Hall conductance. So the thermal Hall conductance is basically if you give a temperature difference in one direction, then you get energy transfer in the other direction. There's a formula that dictates the thermal Hall conductance and make relations to something called the central charge. The thermal Hall conductance is the central charge, which is in this case 1 for the field lowest Landau level, multiplied by some universal constant and multiplied by the temperature. So there are two numbers that dictate, or two indices that characterize the topological phase. So one is the filling number that attributes its electric charge conserving topology, and the central charge is a quantity that concerns the energy or the time translation symmetry protected topology. So now let's try to generalize this to the bosonic version. So as I was saying before, we are only interested in topological phases that are constructed from electrons. So the Hamiltonian should be constructed, should be able to written down as electron local interactions, and then there should be an energy gap in the bulk. So the delta G should be bigger than 0 in the thermodynamic limit. But the state should be chiral, so that on the boundary there should be a chiral gapless conformal field theory that describes the low energy excitations on the edge. So pretty much like the field Landau level, the states should be short range entangled. So this means that the state should not, at this moment, support fractionalization. So there's no fractionalization, and the Quantity degeneracy on of the topological phase is just 1. There's non-degenerate ground states whenever you put it on a closed surface. So the key feature here is the phase is bosonic. So there exists a finite non-zero fermion gap. So what it means is that all bulk and edge excitation below this fermion gap delta F, they must be bosonic. This means that they must be even electron combinations. So if you are going above the fermion gap, then you might get single odd fermion excitations. But if you are below the gap, regardless of whether you're looking at the bulk or on the edge, the excitations must be bosonic. We can also discuss what's the electric and thermal conductance, the charge and Hall conductance, the charge and thermal Hall conductance of this topological phase. So there are some consistency relations or restrictions it must follow, because the system has energy and charge symmetry, and therefore we have the two indices that characterize its topology. So one is the filling number that associate to the electric Hall conductance, and the other one is the central charge C that associate with the thermal Hall conductance. So the short range entanglement, meaning no fractionalization, and the Gaussian-Milgram formula that requires that the filling number nu and the central charge C must be equivalent modulo 8. So this means that they in general might not be equal, but the difference between the filling number nu and the central charge C must be an integer multiple of 8. So if we enforce the bosonic requirement, then this further restricts the filling number and the central charge to be they must be both being integer multiple of 8. And finally, we're actually interested in a case where it is distinguished from 8 field Landau level, which would have both nu, the filling number, and C, the central charge, both being 8. So we're interested in phases that are not 8 copies of the conventional Landau level. So we're interested in cases where the Wilderman-Franz law is violated. So in this situation, the filling number nu is not going to be the central charge C. So this means that the difference is a non-zero number that is a integer multiple of 8. So in this case, if nu is not C, then this means that the topological phase must involve many-body interaction and cannot be described in mean field by a single body mean field Hamiltonian. But so this is the construction. So we can try to first construct using an effective topological field theory from Trans-Simon. So on the left equation here, that's the Lagrangian density of the 2+1 dimensional bulk. So the most important quantity is this K matrix Kij. So here I'm using multi U1 components A field given by small a. And the topology is encoded by this K matrix. So here I will need 8 U1 copies. So this I and J, they are going to run from 1 to 8. And the K matrix is a symmetric matrix with integer entries. And the ground state degeneracy, if you put it on torus, is given by the absolutes of the determinants of the K matrix. So here we are interested in short-range entangled states first, so non-fractional ones. So this means that the K matrix must be unimodular, or in other words, the determinants of the K matrix must be 1 or minus 1. Finally, the bosonic requirement dictates that the diagonal entries of this K matrix must be even. It's a known mathematical fact that the smallest, the minimal model is given by an 8 by 8 matrix that takes a particular form, which agrees with the Cartan matrix of the E8 algebra. So E8 is the biggest hexagonal Lie algebra, and its Cartan matrix is the smallest positive definite even unimodular K matrix one can find. So one can also compactify this notation by looking at the thinking diagrams. So each node, so you can see that there are 8 nodes that corresponds to the 8-dimensional K matrix. So each node corresponds to the diagonal entry of 2, and there are 8 diagonal entries. Each one is 2, so they are represented by these 8 nodes. And each link here corresponds to the minus 1. So for example, if I look at the first node and the second node is connected by a link, so this corresponds to the minus 1 in the 1, 2, and 2, 1 entries of the K matrix. So each time you see a link, this gives you a minus 1 in the off-diagonal parts of the K matrix that connect the n and the n+1 node, for example. So this type of constructions was first proposed by Liu and Vishwanath, but it has been generalized to multiple contexts in topological phases in 2 and 3 dimensions. In particular, we can also make relationship to 3-dimensional topological insulators. So pretty much like the previous case where for topological insulator with a thin slab or thin film with time reversal breaking top and bottom surfaces. So that corresponds to the Chern insulator on the left diagram. There is a other type of topological insulator called the topological paramagnet. So that is not a topological insulator, the conventional one. But if you, in this interacting version, if you break the time reversal on the top and bottom surface, it turns out that you end up with an E8 chiral conformal field theory that runs along the boundary. So we can, in some sense, think of this E8 conformal state as the Chern insulator analog of this topological paramagnet thin film construction. All right. So maybe I should spend a little bit of time of describing the couple Y model. So the model consists of an array of wires, and each wire consists of 11 electron channels. So there are multiple ways. So this is not a unique way of constructing the E8 exactly solvable Hamiltonian, but this is one of the simplest way one can do it. And so the model consists of an array of wires in 2 dimensions, and each wire consists of 11 electrons that can move. Each one can move either in the left or right direction. So I'm going to just denote each arrow line to be a chiral, 11 chiral Dirac electrons. So each wire consists of a pair of these black lines that propagates in both left and right. Because the model is many-body interacting, so it is commonly or more conveniently understood using the bosonized variables. So for each electron operator C, I can bosonize it to be e to the I phi. So this is an electron operator. And then I can perform some unimodular basis transformation. The details are not very important, but it exists some unimodular basis transformation U. So what unimodular means is just that U has integer entries, and the determinant of U is 1 or minus 1. So if you perform such a construction, then basically what it does, it separates the 11 electron channels into the E8 sector and 3 additional fermion sectors. So the E8 sectors are given by these 8 bosons. So this EI, where I runs from 1 to 8, each one of them are some integral combinations of electrons. And in addition to these 8, there are 3 more fermions. But the fermions are not very important. Fermions, we're going to just backscatter in the model. So there's a left sector and a right sector. We're just going to backscatter these 3 additional fermions. So that will give us eventually the fermion gap in the model. So this intra-wire backscattering for the fermions, that's going to get out all fermionic degrees of freedom. And then what we're going to do here is to turn on a magnetic field. The reason for that is to allow us to backscatter the E8 sector between wires. So normally, if you do not have a magnetic field, the right and left sector of the E8 will carry different momentum in the x direction. So if you have a magnetic field under the Landau gauge, then the left mover on one wire and the right mover on the next wire can carry the same momentum, and therefore backscattering them will not violate momentum conservation in the presence of the magnetic field. So if you introduce the inter-wire E8 current backscattering, so that introduces the bulk energy gap. So this gap basically everything out except the dangling modes you have on the boundary. So if you put it on a periodic cylinder or torus, then everything is gapped. But if you have an open top and bottom edge, so on these 2 edges, you will have the gapless EH conformal field theory that runs along them. And because of the fermion gap, all local excitations in this conformal field theories are bosonic. So this page is basically just serve the purpose.
I have a question.
Yes.
So here, this chiral phase, EA chiral phase, which symmetry you're enforcing here? Which symmetry protects this phase?
Yes, it is just protected by charge symmetry, and so charge symmetry just means charge U1 conservation, and also energy conservation.
So if we break a U1 charge conservation, what happens then?
You will still have the E8, but then the E8 the charge. So for example, I think in our case in the paper that we published a few years ago, that's a superconducting phase. So you will still have the E8 phase. You will still have bosonic excitations, so it's still a bosonic topological phase. But the charge part is just gone if you violate charge conservation. So in this case, I focus on both charge and energy conservation because I want to make connection to the field Landau level or quantum Hall states. But in general, if you just focus on topology, that's not a necessary requirement.
Okay, then in what sense this is the topologically protected phase?
It's protected by charge symmetry. So if you do not have the charge symmetry, you cannot really talk about the filling fraction or the filling number. So then all you have is the central charge 8. So here is symmetry protected by the charge U1 symmetry because you can see that it's not 16 Landau levels or it is not 8 Landau level, because if you have 8 Landau level, both nu and C would be 8. So in this case, it's not because nu is 16 and C is 8, they're different. And because of the charge U1 symmetry, you allow both nu and C to be present. And they are not equal, so that in that sense, it's a symmetry protected topological phase.
Okay. Thank you very much.
Okay, so right, so maybe I can also spend one page on summarizing the Wessel-Minowitten algebra. Though the E8 algebra contains 240 operators, so all of them are spin 1 bosons. It's actually not too difficult to understand them using the bosonized variables. The 8 Cartan generators are just given by dx phi theta, where these phi theta are the generators for the E8 root, simple root. And the other roots of the E8 or the 240 roots of the E8 are basically combinations of the simple roots that are spin 1. So if you count them all, then you get 240 roots. So you have 240 operators that are combinations of the E8 simple roots that have spin equals 1. The most important observation in this talk perhaps is the fermionic representation. So that requires us to perform a secondary basis transformation that go from what we call the Chapelle basis to the Cartan-Weil basis. So these are Dirac fermions, but they're actually non-local Dirac fermions because this R matrix contains some 1/2. So the R matrix, the only requirement of the R matrix is that it diagonalizes the E8 K matrix. So there are multiple examples. No matter what you choose, you will have some 1/2 in your R matrix, and therefore your Dirac fermions will not be local. So this means that they are not integral combinations of the electrons. So using these non-local Dirac fermions, you can find a different presentation, but equivalent presentation to your E8 current operators. So the Cartan generators are basically just given by D vector D, where D are the non-local Dirac fermions. And you can separate the E8 roots into SO16 roots. There are 112 of them, and then you have 128 even spinors for SO16. So this basically constitutes all the local bosons you have in the model. So how much time do I have?
You have 10 more minutes.
Yeah, okay, so maybe that's good. So then I can move on to the next part of my talk. So that's on the bosonic analog of fractionally filling the Landau level. So we have discussed the bosonic analogy between the E8 state and the fermionic Landau level. So the next step obviously is to maybe consider what states corresponds to partially filling the Landau level. So this would correspond to states that are partially occupying the E8. So mathematically, this is given using the language of subalgebras or embeddings in E8. And the result is that it will give us a long-range entangled fractional state. So pretty much like the Laughlin 1/3 state, which supports fractional excitations. The bosonic versions also support some fractional excitations. And there will be some particle hole symmetries or particle hole conjugations that I'm going to discuss a little bit later. So maybe I can make one page connection to the case for partially filled Landau level. So in this case, there are actually many states that partially filled the lowest Landau level. And here I'm just going to only focus on the Laughlin 1/m states. So obviously there will also be hierarchy states. They are all possible, but I'm going to ignore them in this talk. And in particular, in this picture here, I'm only focusing on 1/3 and 1/5 Laughlin state. So I'm looking at the two axes. So one axis and the horizontal axis is the filling number, and the vertical axis is the central charge. So the filling number associated to the electric Hall conductance, and the central charge associated to the thermal Hall conductance. So if you look at the black dot here, that's the filled Landau level with filling number 1 and center charge being 1. And this dot here is the Laughlin 1/3 state. This dot here is the Laughlin 1/5 state. So they carried a fractional filling fraction. So the electric Hall conductance is fractional, but the thermal Hall conductance is not, because they are all described by some U1 conformal field theories with different levels. And U1 conformal field theories, they all have central charge 1. So they have the same thermal Hall conductance as the filling 1 field Landau level. So there is a particle Hall conjugation. So instead of consider particles of the Laughlin 1/3 or 1/5 state, we can consider holes of the 1/3 and the 1/5. So in other words, we can start off with the field Landau level and then subtract from it 1/3 of them being holes or 1/5 of them being holes. So in that case, we get the 1 - 1/3 state and the 1 - 1/5 state at the below. So they now carries the filling fraction 2/3 and 4/5. Because they're 1 minus 1/3 and 1 minus 4/5. What it means is that on the edge, they're actually counter-propagating modes. For 1 minus 1/3, there's going to be a forward propagating Dirac fermion mode and a backward propagating 1/3 mode. So both of them carries the same thermal Hall conductance, and therefore they cancel. So overall, there's no thermal Hall conductance. So the overall chiral central charge is 0 for the particle Hall conjugates of these two states. So in general, there's going to be a particle Hall symmetric point at central charge 1/2 and filling fraction 1/2. So for example, this can be the composite Dirac liquid, or in the gapped case, it can be the particle Hall symmetric Fabian state. So all the states that are related by particle Hall symmetry are basically 180 rotation about this red dot, the particle Hall symmetric point. So for example, the 1/3 state is particle Hall symmetric to the 1 minus 1/3, and the 1/5 state here is particle Hall symmetric to the 1 minus 1/5. So what I'm going to do here is to generalize this picture to the bosonic version. So here the black dot is the bosonic analog of the field Landau level. So that's given by the E8 quantum Hall state. So it has filling fraction 16 and central charge 8. So what we're going to do here is to consider some partially filled version of the E8, and we can discuss what type of filling numbers and central charge this state carries. Okay. So you can see that in this case, I'm going to make use of the conformal embeddings or the subalgebra structures of E8. So for example, there's some subalgebra like SU3 or SU2 or E6 or E7. These are some exceptional subalgebras of E8. There's also a G2 and F4 state and some SON level 1 states. So they all carries different filling numbers and central charge. And in terms of the topological orders, there are 3 or 4 types of topological orders. In this table, I only listed 3, but this table is actually not exhaustive. So in this table, there are 3 types of topological order. The blue dots, they're all abelian topological orders. The red dots, they carry some Ising-like topological order, meaning that they carry some Ising anion excitations. And the orange one, the G2 and F4, they actually support Fibonacci excitations, which are universal, which are powerful enough to construct universal topological quantum computers. So the construction is the following. So we are going to make use of a bipartitioning of the E8 Wilson-Miller-Witten algebra. So we're going to decompose this into 2 decoupled subalgebra A and B. So in the conformal field theory language, it just means that the A sector and B sector operators, they must mutually commute. And the energy momentum tensor of the A and the B sector adds up to the energy momentum tensor of the E8 sector. So the couple Y construction is pretty simple. So what one has to do is to first do the same thing we have done before under the U matrix basis transformation to decompose the electron wires into some E8 sector. And then we're going to separate the E8 sector into the A sector and the B sector and let them backscatter in different directions. So for example, in A phase, we're going to backscatter the B current within a wire, and the A current is backscattered between a wire under a certain commensurate magnetic field. So under this construction, in the bulk, you can see everything is kept out, but on the edge, you leave behind the A conformal field theory. One can obviously construct the B phase by just reversing the backscattering roles of A and B. So in this situation, if you construct the different phase where the A and B sectors are backscattered in a different manner, then you get the particle Hall conjugate. So in this case, the A sector is going to be particle, or the A theory is going to be the particle conjugates of the B theory. So the partition function, the bipartition we're going to consider and focus are given by the following examples. So there are different names in different contexts. In the conformal field theory context, these are known as level rank duality or conformal embeddings. Or in the topological phase context, these are known as anion condensations. So all the algebras I'm considering here are of level 1. except for the final two cases. So for example, I can have Ising topological orders by partitioning the E8 into two SON and SO8 minus n sectors. So there are exceptional cases with E6 and E7. These give us abelian phases. And then there are the G2 and F4 decomposition that give us the Fibonacci phases. And finally, there are some other exceptional cases that give us orbifold versions. And the final case are actually the fourth case that I have not discussed in the previous slide. So this gives us the metapletic phase that corresponds to the existence of parafermions. Right. So so this is a different slide that summarizes the different topological phases with different charge assignments for different decompositions. For example, I can focus on the lower left diagram. So these are the exceptional cases for the decomposition of E6 and E7 inside E8. So you can see that actually, even if you start off with the same decomposition, so for example, if I look at E6 cross SU3, there are actually multiple inequivalent embeddings into E8 that give us different topological phases with different Filling fractures. So for example, in this case, I have a few of them. So for example, this E6 here is conjugate to this SU3, but they're actually different embeddings. For example, I can have E6 here or E6 here that have different Filling numbers. And that corresponds to underparticle symmetries correspond to two different SU3 states. Right. And I think I'm going to skip the charge assignments. So we also exhaust all possible cases for the anion excitations and discuss and tabulate their charge assignments, basically the electric charge for all anion quasi-particle excitations for all these states. So I'll leave you with the conclusion. So what we have discussed today is there are two things. One is the short-range entangled E8 quantum Four state. So this is the bosonic analog of the field lowest Landau level. And the second one is the fractional bosonic fractional quantum Four states that fractionally occupy the E8 state. And this is basically the bosonic analog of the partially filled Landau levels. So there are some related bosonic orbifold phases that are perhaps related to Munyip's questions that involve either charge symmetry breaking or some other symmetry breaking. So they give us spin liquid or superconducting phases that has relationship with orbifold structures. So thanks for your attention.
Thanks for the nice talk. So we are looking for the questions. So we have question from Professor Sakbom Jung.
Yeah, Jeff, thanks a lot for wonderful talk. My question is, I have a rather low-level question. So in interior quantum Hall model, I mean, there are various exactly solvable models as you have listed. Yes. So I'm just wondering, do we have similar exactly soluble model either in, well, maybe not in free electrons, but at least in spin for this E8 quantum Hall state?
As of now, I only have couple-wide versions. So if you're happy with a couple-wide, highly anisotropic exactly solvable model, then yes, I can write down a spin liquid model, either from pure spins or from electrons, by gapping out the charge degrees of freedom of the electrons, but leaves with the spin degrees of freedom that allow us to construct from it the E8 spin liquid state. So the answer is yes, if you allow me to use couple-wide model. If not, if you want me to use a lattice model to give a chiral E8 state, as of now, I cannot do it right now. But I suspect, because this is not exactly solvable if you put things on a lattice usually. So I do not have an exactly solvable model, but I can perhaps use the couple-wide model to motivate a numerical model. One can check in using perhaps thin porous DMRG to see whether it corresponds to an E8 state. So I think that can be done and has not been done as far as I know.
Okay, thank you very much.
Any other questions? I have a question. So, Jeffrey, let's say we do this survey of this mapping of a new and C axis using other unimodular group, like not E8, but like a larger unimodular matrices.
Yeah.
Then do we have some like a generic structure of this survey? Or I mean, the symmetry structure in terms of this?
Yeah, that's a very good question. And I honestly do not have an answer for that, because if I just stare at this diagram right now, other than the particle hole symmetry, which is the 180 rotation about this midpoint, I really cannot see any obvious structure in this diagram. And I cannot say the same for the other unimodular base points, like the leech lattice or some monster group CFT. So there might be some additional internal structure in addition to the particle hole conjugation. So it is possible, but I cannot point out any known one at this moment.
Okay. Can you explain me one more time why this 180 rotation occurs in this table?
Yeah, it's basically because of the way we construct the states where we bipartition the EA state. So for example, if I focus, I'll go back to this construction here. The A phase and the B phase are related by subtraction from E8. So like if I occupy the A phase by particle, then this is particle hole conjugate to the state where I first start off with the E8, and then I subtract from it holes that occupy the B phase. So these two phases are the same.
I see.
So in other words, there is a bulk boundary correspondence where in the bulk part is particle hole conjugation. In the boundary part is really coset construction from conformal field theory, where if I just look at this equation right here, the A theory is just E8 quotient B. It's just E8 mod B coset. So in by construction, these are particle hole conjugation states. It's just that it's unconventional particle hole symmetry, because usually particle hole symmetry in the quantum Hall context start off with the base point being your field Landau level. So it's particle hole conjugation based on the field Landau level. Here we're not based on the field Landau level, we're based on E8 state.
Okay. Thank you very much.
Thanks.